Hi, what we're presenting here is a low-cost platform for prototyping, testing, and speed characterization of digital circuit IPs. This work has been developed in the VLSI Design Automation Group at King Fahd University of Petroleum and Minerals in Dhahran, Saudi Arabia. Circuit IPs really represent great opportunities for circuit designers, researchers in universities and small companies. The problem is that before they can market their IPs, they really have to silicon-proof them. And to do that, they basically design a prototype IC, have it fabricated, then when it comes back, they need to test it and characterize its speed. The problem, this would require high-speed test boards, high-speed testers, pattern generators, scopes, etc., etc. These are not only expensive, but they actually require additional design skills that many people in universities might, or many circuit designers might not have them, like designing high-speed signaling boards. So what is really needed by IP designers is, first of all, simplicity. We want to allow IP designers to test and characterize their IPs without actually having to design any special type of test circuitry as in BIST, or having to design a special test board and fixture. Also, the platform must be programmable so that they can easily describe their test and characterization procedures and maybe even include some kind of a software in the loop. This is where our test and characterization platform, TASIB, come into play. So actually it has two main components: a test support circuitry that is to be included with the IPs under test, what we call IUTs. So on the prototype chip we have this test support circuitry, which actually allows us to test unlimited number of IPs with unlimited number of input-output ports. It also provides a fixed interface to a specially developed test and characterization processor, which can be implemented on an ASIC or an FPGA, which in turn has a fixed interface to the user PC, where we have an interface software running there. So this setup here allows us to test any number of IPs with any number of IOs, and the tester, the user, can specify his or her test procedure, test data, get test results, control the onboard or on-chip clock generator, increase the frequency, reduce the frequency of test, do whatever they want. Also, to go along with that, as I mentioned, we have several software components. We have a special software that will take the user's IPs and generate the required support circuitry to be included on the same test chip. Also, we have a user interface software that allows the user to program their test procedure, input their test data, get their test results, take a look at all the memory contents of the processor, the registers, and so on. Okay. We also have another tool for developing test programs graphically. This is a snapshot of the test support circuitry generator software. So as you can see here, these are defined by the user. These are basically the IPs that will be on the chip. For each IP, they describe their input-output ports, the types, what kind of control signal they want, and so on. And this software will automatically generate the Verilog file for the complete test chip that can be taken through a typical synthesis and place and route design flow. It's worth noting here that if some of these IPs have been generated as hard IPs, meaning custom layout, they can just be designated as don't touch in the synthesis flow. So this is a typical flow. The user will take their IPs, use our tool to generate the test chip with the test support circuitry, go through synthesis, place and route, send it for fabrication. Once it's back, they can just simply insert it into the socket on the test board and start testing their. So this is actually an image of our developed test board. As you can see, it's about 2 inches on the side. We have provided several SMA connectors that are connected to fixed pins on the chip, so that if the user wants to get an external clock into the chip or some other signals or get some signals out, they can still do that. This is a photograph of our prototype chip, actually. As you can see, it's very small. It had just 4 IPs along with the test support circuitry, along with a configurable clock generator with a DCO. This is under the direct control of the user, where they can program it to give any frequency they like. So they can read the frequency, increment it, decrement it, and so on. Now we will see a live demo of our test and characterization platform. This is our prototype chip inserted on the socket here in the test board, which has 2 interfaces to 2 popular FPGA boards actually. through this interface is connected to an FPGA board that contains a prototype of the test processor. This is a very low-cost FPGA board. It's connected to the user PC through a serial port or serial communication. In the future, we plan to place the test processor as an ASIC here on the same test board with the chip being tested. This is the user interface software that allows the user to write the test procedure as a test program, specifying whatever test they want to apply, to select one of the IPs on the chip, apply whatever test they want. It allows the user to download the test program to the test processor, upload it again to check if it's correct, to view all the register contents, to view all the memories on the test processor, all their contents, download new contents, upload them, even modify some parts and download them again. This test program actually, it loops trying to find the maximum operating frequency for one of the IPs, so it applies the inputs. If the results are correct, it increments the frequency and keep doing that. As you can see, these are the different frequencies on the right hand side here that are being applied. We're running it in single cycle mode just to be able to follow up with the execution. Also, all the register contents are being dynamically updated. All the flags resulting from comparisons between received data and expected results. So the program keeps running until it's done. This is a screenshot from the user interface software for the previous live demo actually, which was to determine the maximum frequency of operation of one of the IPs. As you can see, this is the maximum frequency measured, 735 megahertz. Now, for this specific frequency here, we will show an output of a DCO actually on a scope. Here is it. So this is showing the measured frequency from the scope compared to the measured frequency from the actual platform, which match very well.